I will briefly explain why we are doing this round-robin test and give you a short introduction into the ice. I will explain why we have chosen silica gel as a first material. I will introduce the measurement protocol and the way we exploit the data. Afterwards, I will show some data and measurements delivered by all participants, which parameters has been used, and discuss the differences. During our last IGC Symposium 2019 in Cologne, an open discussion highlighted the need to prove the reliability and robustness of IGC. In particular, the use of a reference material was mentioned, but this was not the first time that such a discussion was occurring. The reason was quite simple. For IGC, we have no reference, no standard, no normalized data explanation, no standard analysis. Hence, each published IGC result is dependent from the operator. Of course, this delivers a negative picture of the technique and makes that the results are considered as not reliable. Therefore, we started a collaborative work in order to develop a good practice for IGC measurements. This can be considered as a first step of normalization or standardization of IGC measurements and analysis. A round-robin test is ideal to compare results obtained at several institutions with different setups and compare these results to try to understand observed differences. And in addition, this can be a starting point to develop a first reference material, for IGC. The goals of the project are to check and prove that IGC is a reliable method, hopefully not dependent on the system or instrument, test the first reference material, therefore it has to be chosen and a valid measurement protocol has to be defined. Compare the obtained results. Here we are at the point to identify, discuss and understand differences. But this helps us to define good practices for experimental setup and protocol as well as for the data exploitation. Last but not least, it is important for us to develop an IGC community, to have discussions and to improve our knowledge. We are very happy and thankful that 16 laboratories and companies participate in our test. These participants are coming from 7 different countries: France, Germany, Poland, China, Lebanon, Czech Republic, and Portugal. Unfortunately, due to different reasons, just 12 participants were able to take part in the first step and send measurement data. The first step of our study was to choose a material and to develop a measurement protocol that takes into account all different setups. We have participants using own build systems, some are using our ACIENTES approach solution, and some are using surface measurement systems. We did not want to make it too difficult in the first step and had to choose a good material that is suitable for all participants, as some are limited in the temperature range or in the column length. At the very first beginning, ACIENTES tried different materials. ACIENTES started with PVC, but the problem was that it has a low surface area combined with low interactions. So this requires high quantities of sample that could exceed some capabilities. The second try were 2 different BT surface area standards from BAM, titanium dioxide and alumina dioxide. But both are difficult to measure as they are very interactive and they are fine powders that have to be compacted before introducing into a column, and this could generate first deviations in the results. Finally, we went back to the materials that was already suggested during our previous symposium in Cologne, the silica gel. This material provides an easy filling into the column without special preparation. It is available in large amounts and it has an increasing difficulty in measuring. That means that the alkanes are quite easy and fast to measure, whereas polar probe molecules can get more difficult, what we will see later. So we proposed the following protocol. We asked the participants to use silica gel with a mass of 0.285 gram in a stainless steel or glass column with 2 millimeter inner diameter and a column length of 15 centimeters. The conditioning at 130 degrees Celsius for 16 hours. A measuring temperature of 120 degrees Celsius at a flow rate of 20 milliliter per minute. Methane should be used as a reference, and linear, branched, cyclic alkanes and polar probe molecules should be measured. The current status is that we got 17 measurements from 12 participants. So also reproducibility measurements were performed by the participants. Often the proposed protocol was not exactly followed because each user has different habits and know-how. This leads, for example, to a different column design in material, length or diameter, but also different flow rates have been used. But this is not negative. We see this as a point, as a possible point to open the field of parameters to investigate. So we get more input by these deviations from the protocol. Each participant gave us information about the experimental setup, the net retention time, sample mass, flow rate, pressure drop, and any other observations. The data we got look like this. We have the setup with all the informations with which system the measurements were made, the pressure, temperature, and any additional informations. And below we have the net retention times. For this data sheet, it looks very good as we have, as the retention times are very reproducible at various injections and molecules. We have very low deviations for the alkanes, and also the polar probe molecules deviate not that much. All these collected data from the participants were analyzed by one person to exclude differences in the analyzers. And of course, all calculations of the retention volume, the surface energy, and the specific interactions were performed according to the same algorithm. Now I want to come to the data, measurements, and results. All data and results are anonymous. Each number stands for one institution. If an A, B, or C is added, these are measurements from the same institution as reproducibility tests. The only exception is participant number 3, A and B. Here, significantly different sample amounts were used. As I said before, the participants had chosen different experimental conditions. In fact, we saw that different types of columns had been used. Of course, some participants have used the stainless steel column with 2 millimeter inner diameter and 15 centimeter length, but other participants are using Teflon columns with 2 millimeter inner diameter and 33 centimeter length. This was a bit surprising because with the same internal diameter, we have a much longer column. This can be the result of a different packing, or this can lead to larger dead volumes in the column. Other participants are using glass columns with fixed column lengths. These 30 centimeter glass columns are almost completely filled with the material. One participant used two different columns with different inner diameters of 2 and 4 millimeters and very, very short columns with 5 centimeter length. And in fact, it is interesting and important that all participants use quite the same sample amount with this one exception. Here we have another summary of the experimental data. You can see that the corrected flow rate varies. The variation were caused by a little misunderstanding. So we have flow rate values between 5 up to 20 milliliter per minute. For participant number 11, 20 milliliter per minute was indicated. But as you can see from the pressure drop on the right-hand side for this sample, it is that the pressure drop is quite low compared to other columns with the same filling and length, like column number 1. Also, the retention time of this participant number 11 are much larger, as we see later. So our feeling was that it was just missed to change the flow rate from the activation to the measurement, as the activation was done at 5 ml. Overall, the variation in the flow rate and the variation of the column geometry leads to variation in the pressure drop, although we have similar sample mass. Many participants are in the range of 600 to 700 torr, but we have also deviations like number 3B with very low pressure drop due to small sample amounts. But we have also more challenging observations, like these of participant 1, A and B. Same column material, geometry, and sample mass, but significant differences in the pressure drop compared to number 4, A and B, with the same setup, that have exactly the same pressure drop. So, with this in mind, we can make a first estimation which experimental parameters can have an influence on the observed results. On the left-hand side, we have parameters that have not been checked till now or in this first step, but I will briefly give a comment on them. The instrument can have a little impact, especially at higher dead volume. This can play a role to increase peak broadening. The sample amount has not been checked, as everybody should introduce the same amount of sample. But what we see on the short column is that just this column with 80 milligram filled can have an impact. Too low sample amount can lead to a bad chromatographic behavior due to not enough theoretical plates. Or it can also happen that you are not working in infinite dilution anymore with less sample if you don't adapt the injected amount. We have fixed the conditioning and measurement temperature, so we can't investigate this. The injection amount can have an impact, but it's difficult to discuss now. What we can examine in the first step is the influence of the flow. The dead time determination, the determination of the retention time can be investigated, as you have two possibilities to measure or analyze the retention time by an integral method or by the peak maximum. The pressure drop can be examined. We can also have a look how molecules with very short retention time can influence the results, as small differences in low retention times can have a big impact on the results. We are comparing here the retention time of octane. You can see that they are varying a lot between the participants, but this is normal as we have used different columns and flow rates. So comparing retention time is not that meaningful. A more standardized way for comparison is to use specific retention volume, because that is normalized for carrier gas, temperature, and mass. But we see that there's also a variation of up to 30%. This was surprising for us. Reasons can be how the carrier gas is measured or controlled and how the carrier gas is corrected. This is important as the flow goes directly into the calculation of the specific retention volume. For the retention time of polar probes, it is even more difficult. Here you can see our most complex probe molecule in this test, the acetonitrile. The complexity can already be seen on the chromatogram I will show you on the next slide. So we got very different results, retention times from 13 up to 177 minutes. Our idea is that this is a result of two different reasons that such big differences occur. The first is the different way of exploiting the peak to get the retention time. I will explain this further in the next slide. The second reason is that different amounts of probes are injected that cause very big variations and that needs to be further investigated. It has to be tested how a target variation of the amount of injected probes leads to different results. So we have to check this properly in the next step to get more reliable results. But again, this was the most complex molecule in these investigations. Don't be afraid in your analysis, as single molecules can be excluded from your analysis. We also got good reliability for polar probes, but we can learn more from these differences or complicated molecules than just showing the easy and measured without problems probe molecules. Here we have two different examples of polar probes, dichloromethane on the left-hand side and acetonitrile on the right-hand side, measured on two different systems. You can see that the peaks are very different. The acetonitrile peak is very asymmetric, and the exploitation of this peak has an impact on the determination or on the determined retention time. Below, we have shown the peak maximum method, where the retention time is here. In the upper case, we use the calculation of the center of mass, and we have the retention time here. We see that the way you analyze your chromatogram has a big impact on the result, and that this has to be discussed in detail in the next step of our tests. You can see that dichloromethane is much easier to analyze. In general, it is important for a correct exploitation of the data to have a good baseline, a low level of noise, and a valid retention time determination. Here we have calculated dispersive components of surface energy from all participants. We see that the results are relatively homogeneous, but we have also some outliers. 11 measurements are in the standard deviations and 5 are off. For some measurements, this can be explained quite easily. For others, there are still open questions. We have a median value of about 34 millijoule per square meter. At first, we want to look on number 1, A and B. We have a good reproducibility. Also for number 4, A and B, we have a good reproducibility, but these values are a bit off or are a bit low. It can be said that number 4 is a university that uses a special way to determine the dead time. And also the dead time can influence our results of dispersive component of surface energy. 1 second difference in the dead time, for example, can have an influence of up to 2 millijoule per square meter. So we see that this can have an influence and needs further investigations. For number 3, A and B, the results are very different. This is a result of the low sample amount for one of these samples. We have not enough theoretical plates and bad chromatographic behavior, so an underestimation of the surface energy. We have measurement 7, that is a bit higher, where we have no real explanation at the moment. So most of the outliers can be explained and improved. That is the good message. We also want to comment on the laboratories that are using our Acientis approach. We are very close to each other with a mean value of 34.4 plus minus 0.9. But with this, we don't want to claim that we are working better, as we cannot say this is a real value for the dispersive component of surface energy. But what we can say is that we have reached a high level of standardization with our solution, as different people at different locations get the same results. The last topic is the specific interactions. We have a lot of variations for acetonitrile, as already discussed, even for internal reproducibility tests with the same conditions like for A and B, we get different results. This is related to the peak shape of acetonitrile that is very asymmetric, as we have seen. And in addition, it indicates that the injected amounts of acetonitrile has an influence on the retention time. And coming from that, the specific interactions. So one task is to make these kind of difficult measurements of such strongly interacting probe molecules more reproducible and comparable. But the good news are that we also got reproducible results also for acetonitrile, like 1, A and B. In contrast to acetonitrile, dichloromethane is much more homogeneous because we have a shorter retention time and the peak is symmetric. This makes it much easier and leads to good values and reliability. It is important to mention that these specific interactions are used for further calculations, like we have heard, the acid-base properties. To conclude, from our point of view, the first step of this round-robin test was successful. We saw a lot of variations that can help us to improve, but we have seen also good reproducibilities, especially for the dispersive component of surface energy. Also, new challenges and questions occurred that have to be considered for further developments, like column filling, determination of dead and retention time, check the amount of injected molecules, especially for probes, and further or more materials have to be investigated. And with this, I would like to thank you for your attention.